Hello, welcome to SafePete.net Meetup. I'm John Calloway. We've got Clayton Hunt in the back. We are your hosts for this evening. We are having David Crook speak about Data Science 101. Come back next month and see Intro to Document DB in Azure. I think what else we've got to thank our sponsors, of course, the Iron Yard, Tech Systems, as always, for bringing our food. So wave your hand, Tech. Hello, everyone. So if you were seeing your notes, we've got some giveaways from Rock's Books and Pluralsight this evening. I think we might be out of JetBrains licensing, but we'll try to get in contact with them and have some more giveaways next month. So with that, start you off.
Hello, welcome. So this is Data Science 101. I also like to put a focus on to production. I've seen a lot of talks on data science, and it doesn't necessarily involve getting that data science into production. So this is going to be more around building data science systems and getting those out to production, and what does that look like. I'm David Crook. You can follow me at data4bots. I'm trying as hard as I can to grow my Twitter following. I did not win this year's competition. In my group, we're all about evangelism and like growing our following, so forth and so on. Unfortunately, like my buddies who do video games are a lot more popular than like me who does like algorithm development. So like they won, and I'd really like to win this year. So if you follow me, that would be really amazing. So you don't even have to listen to what I say. Just follow me and just ignore. That's fine too. So my website is dacrook.com. Basically, when I'm writing code or whatever and I encounter something challenging, I end up writing an article more for my reference, but it turns out that a lot of other people encounter similar problems, so maybe you can use it for your reference too. It's just like consolidated notes and stuff. My PowerPoint's not working. Oh, come on. There we go. So I can't do a talk without doing at least one or two plugs. One of the things that I've got going on this year is actually a really cool thing for anybody who's building a project with any cutting edge Microsoft technology. I'm a dev lead for the machine learning group, and we're looking for projects. Basically, we do them for free. It's within a certain scope and stuff. So if you're using some of the latest Microsoft technology to build a new project and it involves any sort of intelligence and it's going to have some form of cloud component to it, please be sure to shoot me a note either via Twitter or my email address, which is dacrook@microsoft.com. So that's really cool. Basically, it's get some Microsoft engineers to build some stuff for you for free. Then there's this data-FL Slack channel. How many people know about Slack, know what Slack is? Has heard of Slack? Raise your hand, like higher so I can actually see who you are. Cool, okay. So this data-FL Slack channel, shoot me an email if you want an invite to that. I'm basically making a Slack channel for any data developers, machine learning folks, data scientists within the Florida area. So you have like an area where you can get some free help. There's all sorts of stuff pops up on there. Like the other day, somebody was having some issues doing some numerical computing. Somebody else popped on and said, oh yeah, you're missing like the shape of your array is wrong. So they went and they fixed it and it was pretty cool. It's kind of like a more tightly knit Stack Overflow kind of thing. But most just people focused in the Florida area. And then I did release this R Jumpstart thing. I know Microsoft has released a lot of R into the ecosystem lately. So I went ahead and just recorded I think it's a 4-part series on R. It's a deep dive, like we're gonna go through data structures, data manipulation, how to do visualizations, not like crappy visualizations, but like interactive visualizations that have like hundreds of thousands of points and can be displayed in a modern device and are interactive. So that's pretty cool. It's this link on the bottom. So yeah, those are some core announcements. The other thing I want to announce is that like I like to do interactive sessions. So if, I have some key takeaways that I want you guys to get, and if you don't get that, I want you to know that you should be asking questions. And if you don't ask the questions to answer what I'm trying to get out of this for you, then it's your fault that you didn't learn what you came here to learn, and not my fault as a bad presenter. So I need people to ask questions so you get to know what you want to know. that said, I thought I'd line out what the goals are. So it's Data Science 101. I figured the first thing we should do is, what in the world is data science? You know, a lot of people are using the term. Not a lot of people know what it is. Even less are actually doing it. Data science plus application development. I've seen a lot of data science in its own little realm, and that's cool, but I like to think about what is the value to the business, what am I actually bringing to bear, and how do I actually get that surfaced out to the world in a consumable format. So we're going to spend a lot of time talking about data science in an application development work stream. Building for ambiguity. I've built a ton of these systems lately, and I kind of came up with this way to describe it using like forklifts and presents. So hopefully you get an idea of how forklifts move presents around. Using Azure architecture. So what does this actually look like if you take an actual product or series of products like Azure to build something like this? And then we'll do a couple of quick notes on data visualization as well as algorithm development, which are more on the deeper dive into what data science is and looks like and smells like, because most of the rest of it is really high level. I didn't know anybody's experience level, and it says Data Science 101. So hopefully, you know, we walk away with a high level understanding of this. I tried to keep code out of it. Anything that says 101, my goal is my grandmother can understand it, I did a good job. So you guys have at least written code, you should do better than my grandmother. Thought I'd give a little bit of history about myself. This isn't like the last thing I ever thought I'd be doing as a like a professional. I failed calculus a couple of times, and statistics I think I failed once, and it just like was an accidental data scientist. It turned out that I found a really cool passion in video games, built some backends for video games, did some artificial intelligence for the bots for those games, and then was like, man, this is really cool. How do I make my bots kill more people? So, you know, because you're doing like Call of Duty or whatever, I was making my own little toy games with like tanks and stuff, and I wanted my tanks to start winning their wars, so I had to learn a lot about artificial intelligence. Then I thought embedded technology was pretty cool, and started diving into that a bit, and learning about how sensors interact with the world and how can we derive insights out of those sensors, not just with data visualizations, but how can we take it beyond that into impacting a real system again. So that's kind of like my background and how I got into it. I started learning the math and the science more as an ongoing basis. And it's been kind of interesting doing it that way because I come at it from a different perspective than traditionally. I spent a lot of time just like prototyping, inventing. I just sold one of my businesses for 5%. And then I do Brazilian Jiu-Jitsu in the mornings because that I go crazy if I don't like do that. If you get choked out by like somebody in the morning, that's the worst thing that's ever going to happen to you in the day. So like the rest of the day seems pretty trivial after that. So I always try and do Brazilian Jiu-Jitsu in the mornings. The rest of the day is easy. Okay, so that's all the like overhead talky stuff. So I want to kind of get a dive into what is it. So data science, what is it? A lot of people think of like iRobot or maybe just charts or something. I broke it down into 4 categories. You've probably seen 3 of these categories before. If you haven't seen 3 of these categories before, these are 3 known ones. The first 3, descriptive. And these are usually in the form of analytics. I kind of consider data science as a catch-all phrase for like machine learning, business intelligence, information science, analytics. It's really about the same thing. It's really just a catch-all phrase for I'm doing something smart with computers and not like just some insertion CRUD operations into a database and surfacing that out through a web application. It's how are we doing something more intelligent with the information that we have at hand. And we start off with a descriptive analytics followed by predictive, prescriptive, and actuated. When I encounter these 4 things, it's usually in that order. We have to have step 1 before we make it to step 2, then we have to have step 2 before we go to step 3, and before we get to step 4, we have to have 1, 2, and 3. So here's a couple of slides on what those are. So descriptive analytics. This is, remember I plugged my R jumpstart, you actually build this interactive chart in the R jumpstart. And this was, if you don't know about the open data movement, there's a bunch of open data that you can get, and I went and found what everybody was being put in jail in Miami for. So I thought, hey, that'd be kind of cool to go and do a descriptive analysis exercise. So really what descriptive analytics is taking a look at what you have in your ecosystem, what data you have, and just visualizing it and coming up with some insights. So from here, this was actually an interactive chart. So we could see things like, hey, it looks like whatever this dark red is, disorderly in public seems to peak around the middle of summer in Miami. Well, that might make a little bit of sense. It also turned out that most of those were alcohol related. So, descriptive analytics really at the core is getting to what are we seeing in our ecosystem. It's kind of hard to predict or prescribe if you don't even know what you're seeing. It's like trying to act without senses. Then we've got the predictive. This is a different example. I just kind of grabbed a picture from online that kind of showed what I was trying to talk about. But what you can see here is that we have some descriptive analytics here. We have probably what looks like some form of stock data, ice age, I guess. But we've got a lot of hot, we've got a lot of cold. We're following this trend line average. But it stops here. This is now. We think it's going to go in this area because of what we've seen historically. So it's taking a look at what you've described your current ecosystem, and based on the trends in some form of extrapolated function, you're able to predict what happens in the future. So that's being able to say, things like, I predict that this house might be worth $340,000 because it's close to the beach, it's got 3,000 square foot, it's fairly updated, so forth and so on. So that would be a predictive analytics exercise. You take that to the next step, and you have a prescriptive analytics exercise. So you have an ecosystem. You can predict what's going to happen in the future of that ecosystem. Well, now it's time to prescribe what you should do based on your current ecosystem. Do you buy the house? Do you sell the house? Do you hold on to the house? Do you rent the house? Okay, so you bought the house previously for $400,000. It's now worth $350,000. Well, you probably shouldn't sell it right now. You might be better off renting, because the rental market, based off of your descriptive and predictive analytics, say that you can rent it out for $2,500. Ergo, you should rent, hold on to it, because we predict it's going to get higher in the future and maybe be worth $450,000. That's the time that you should sell it. So that's kind of prescriptive analytics. It takes, the description, the prediction, and then adds that third component to it. And finally, this is the last item, is an actuated analytics. So not only is it going to tell you to buy or sell or whatever, it's actually going to go do it for you. And I thought the easiest way is to showcase that in the form of a robot. I actually got to do some soldering on this specific robot. I'm from North Carolina State University, and we entered into the DARPA challenge. And as an undergrad, they didn't let you write any code. They said, hey, join the robotics club, solder a bunch of BS boards that we have these schematics for, and you have no idea what they're going to do, and we're never going to tell you what they do. So my only real claim to fame on this one is I soldered a couple of boards on it, and that's about the sum of it. But if you take a look at this holistically, you have a bunch of cameras on it, so you're able to visualize and see the information that you have at hand. When you need to generate your algorithms that do the predictions, you're taking a look at the information based on the pixel color, intensity, so forth and so on that's coming from it. You have information coming from the wheels, how, as far as what friction they're seeing, what the brake system's doing. You have a lot of feedback built into the system, and you can describe your current ecosystem, and then you can predict what is going to happen maintaining the specific course. You can then prescribe a resolution. Hey, there's a pedestrian in front of you. You should turn left. And then you can send a message down to the steering wheel to, hey, actually turn left. And then kind of progress from there on out. So, I walked through 4 very different things. We did robotics and ice age and so forth and so on. Very specifically, because it's not just, actuated doesn't have to be a robot. If you take a look at, how many of you are familiar with SQL Azure? Have you guys seen the new index optimizer feature in SQL Azure? Heard of it? Basically, it can collect information on what kind of queries you're executing against the database and restructure your indexes for your schema based on the actual query pattern that's happening. What you're seeing is the result of an actuated analytics exercise. They have information, they were able to describe it, they could prescribe a resolution instead of just saying, hey, you should fix this index like the optimizer wizard, I forgot what the name of that tool was. It says, hey, go and do that. Instead of telling you what to do, it actually goes and does it. So that would be another exercise. So it doesn't have to be robotics, it doesn't have to be anything that sophisticated, it can be anything in a software ecosystem. I want to take questions at this point before we go, just in case there are any questions. I feel like I did a good job, though. I'm usually pretty confident in myself. That's part of that jujitsu thing, is it builds confidence.
How far did the car actually end up going? I know most of them didn't do so well.
I don't know. I just soldered the boards and didn't get to go, you know, like... I was like a freshman, and they say, hey, who wants to build a self-driving car? I was like, I do. And they're like, good, go sit in the corner and solder some boards. So, yeah, my only claim to fame was like soldered boards. I didn't go, I didn't do anything. I did get to see it test, and it was kind of fun watching them test because they drove around with a pickup truck, and the guy had this ridiculously big red button that they would smash if it looked like it was going off course. So I thought, let's talk a little bit more about data science in the wild. I'm going to preface this with a lot of this is based off of my experience and what I've been doing. And remember, I'm an accidental data scientist. I'm like kind of sort of formally trained, I guess, like, throw into the deep end and, figure it out or die. I'm still employed, so I guess that's a good sign. So that's the preface. So the first thing that happens, probably a lot of you have taken a dive at looking at what data science is and tools, so forth and so on, is you get back something that looks a little bit like this. You go on the internet, and this is what my brain thought when I first started into this. I was like, data science, it looks like this cool big thing, and I should learn it because that's the direction everybody's going. And this is kind of what my brain felt like afterwards. I was like, wow, that's way too much stuff. I'm never going to learn it. What direction do I go? And then it turned out that I needed to think a little bit more specifically about what I wanted to do. Pick something to build and go and build that. So, when I first started, it was video games. So we primarily lived on the server. We had some client stuff going on, targeting modern applications. There was a lot of data that was moving really fast. There weren't really any legacy products involved. We had some platform constraints because we were pushing the Azure platform at the time. Legal issues really only pertains to running R on a client device. But you got to kind of think through these series of questions, and you will actually, after you answer these questions, be able to come back with a tech stack and a series of tools that are very useful for these areas. So I'm going to walk through kind of this decision-making process with you real quick. So in my spare time right now, I'm trying to build a underwater self-driving submarine. It's just something fun that work's not going to pay me for, and hey, that sounds kind of cool. I saw this challenge up on the internet for Shell that said, hey, we're going to give you up to $5 million if you can map the ocean floor at 4,000 feet depth, which is about 1,800 pounds per square inch, and nobody's done it, only 5% has been mapped. So I thought, that sounds really cool. It gives me a direction and a trajectory to go with my education. Maybe I can work some Microsoft stuff in there somehow and talk about it and still get my pay. So that's the direction I went. So let's walk through this. So I got to do data science because I got to build some complex algorithms to map the ocean floor, and nobody's done it before. So how do we do that? So I probably have some server technology because I got to store my data somewhere. I'm not going to stick it on my home RAID array, which I just got done telling these two about, crashed on me, and I had to reconstruct the data, and I was like, forget that, I'll stick it in the cloud now. So I'm going to have some server that stores my information. I've got embedded components to it because it's a robot. I don't really have any client technology as far as a phone or anything like that involved. So okay, so we can cut client out. So now I know I've got a server target and an embedded target. So what do I really need to do here? Well, there are some business decisions that we're going to have to make as far as like which way to orient our algorithms. We definitely have the robotics component to it, so we have to have real-time operating systems. And still no modern apps. How much data and how fast? Well, we're going to have a lot of data going really, really fast on an embedded layer, but we're going to have a significant amount of data more in a batch style process going out to the server for training. Okay, so once we figured out those kinds of things, we kind of get a map of what kinds of things we need to run where. Are there different stages in the pipeline as far as like how data moves and how fast? You know, are there longer term predictions and immediate predictions? Well, you know, if we need to avoid an object because we're building a robot that has to avoid like the floor or something, well, those are immediate decisions you have to make right now. And then, you know, maybe if you're trying to find an octopus or something that's like super rare, you know, you don't necessarily need to make that decision immediately, but it'd be nice to make it as soon as you see it. So you've got a little bit of a slower path of information travel. So, you know, you're starting to think in these high level kind of movements. Legacy products involved in the ecosystem. Okay, well, for me, I'm building this underwater robot. If I am targeting the US government, there's probably going to be a legacy product that runs Fortran or something involved, and maybe COBOL and a mainframe. So I probably need to at least consider that that's a potential item. Platforms that I want to use, well, I'm really good with Azure, so let's start thinking about things that run and operate on Azure. And then are there any legal issues? Well, the only legal issue with this is I can't directly bind R code on my embedded platform because of the licensing model for that. So that creates a little bit of a hiccup. That means I'd have to run through like an execution engine, which means I can't use that on my hot path. So, okay. So I got this map in my head, and you know, it probably realistically looks a little bit like this still. And you just heard me describe it. It probably sounds a lot like this, right? How many of you feel like this right now? Raise your hand, it's fine. You don't have to be shy. But that's how we're thinking, right? Some common scenarios. These are things that I've seen very commonly as far as like high-level breakdown. So if we think about this particular scenario with the underwater robot, it's a greenfield intelligence solution with an embedded platform. You probably have a greenfield solution with mobile phones, possibly server-side microservices. Maybe you've got some BI that you're trying to do where you're going to deliver that intelligence to mobile phones, maybe microservices with simple data sources. Simple data sources I'm defining as like Oracle or a SQL database, something that's common that's out there. It's probably structured information. Complex data sources would be like you've got third-party data stewards. Maybe you're dealing with like a foreign government who says, no, the data is not allowed to leave Ireland because we're Ireland and you're not allowed to have anything that was generated in Ireland. I don't know if Ireland does that. I feel like they did that at one point, but since I'm on camera, I'm going to just kind of say that I don't know if Ireland actually does that. I just picked on Ireland. I don't have any Irish friends, so there's no point for that. So anyway, so you got those kind of things, and you can have a couple of combinations of them. So this is kind of what I ended up with. This seems to hit pretty much everything if you combine those. So these are some technologies that you should probably think about having in your ecosystem if you don't already have those in your ecosystem. From just a languages perspective, let's start with this. Microsoft R Open. I almost always start with this whenever I get a data set. So if I have existing data, either simple or complex data sources, R is a really good target. It's super easy to use and learn. It's interactive. The code like clarity is really nice. So it's really easy to get up and running and just get your descriptive and data understanding and your initial insights on what the heck you're even dealing with when you encounter something out the door. The nice thing is that if we go back to this one, if we're doing greenfield, these two, or these two, as long as we're not going embedded, I can pretty much copy paste any of that initial discovery code that I wrote and put it into SQL Server 2016. Or I can deploy it to a Spark Hadoop cluster. Or I can deploy it to, what was the name of that server? Shiny. There's a couple of other like hosters that bypass a lot of the legal issues that are involved with the R language itself. So that's really good. I mean, I can start here, and no matter what direction my project goes, even if it's embedded, at least I have a quick way of getting up and seeing what I have to contend with in a nice way. Next, I either choose F# or Python dependent on the scenario. If I have a mobile phone target and I don't have to go embedded, I'm probably going to pick an F#. If I have to go embedded and I may not have a mobile phone target, I'm going to go Python. That said, both of them can target each other, embedded as well as mobile phones. It's just a matter of the complexity of actually getting that code to the target device. So Python, if you want to get it into like a Xamarin application, you can convert that into C code, compile it into the number of targets that you need, and then reference those as native libraries from your Xamarin application. F# you can just write a F# Xamarin application from scratch with F#. So like super easy, as opposed to going through this whole like other layer, right? Whereas for embedded technologies, this can produce C that can be consumed by a lot of the real-time operating systems. F# is a little bit more complicated. For the NVIDIA embedded boards that I've been targeting lately, I haven't found a good solution for it, so actually I've been going more Python in this area. And this is for production services for the intelligence portion of those services. So when you look at like C# versus an F#, I have a whole talk that's like really long on the C# versus F# thing. But basically there's a lot of really great numerical computing, distributed computing, and some really nice and tactical things for this kind of complex pipelining and numerical computing type processes. That makes F# a little bit easier to write and deal with and manage over time as opposed to C#, and they both are .NET, so they kind of work happily. I can write F# code. My C# developers have no idea until they're like, hey, let me just look at what David wrote. Holy crap, it's F#. What do I do with that? So, you know, when I get to that point, they're a little upset, but they have no idea unless it breaks. So just don't write code that breaks and you'll be fine, right? So anyway, C# is into the integration of everything. If you look at like the way that Microsoft has been releasing products, it's always C# first, right? So .NET Core, ASP.NET Core, those are all C#, can't get F#. So C# ends up being a lot on the integration front as far as systems integrations for getting your data science applications out there. And C# can consume C, and it can consume F#, and it can consume R. Typically you deploy your R into its own microservice, which C# calls out to. A lot of these will get deployed out as far into like a microservices architecture. So C# ends up being kind of like your glue for everything. Devices, C, C++, most real-time operating systems will operate off of C++ or Fortran. I don't know Fortran, so C++ it is. And then deployments, either on-premise or Azure, all those will work across the board. Just be careful with anything on-prem with R. Just read the licensing agreement. I got into trouble. That's why I'm all about our licensing agreement.
Is that licensing agreement a Microsoft issue, or
it's an R issue? Yeah. So like, if you read through it, there has to be like a distinct layer between how you ship the R code. So like you can ship R code, but it has to be called from like an execution engine. So even if you do SQL Server 2016, Microsoft got around that by having this like translation and execution system between Revolution R's services and SQL Server. Otherwise, you can deploy it, you just now have to open source SQL. So like, I don't want to do that. I don't want to open source the product that I make my main money on to the world so that my competitors can steal that and go make money on it, because I don't market very well. So somebody else who's better at marketing has all your code if you run into that situation. So just be careful. Just read the licensing agreement for anything that's open source. And a lot of times, like, you'll find like Python is open source, Ubuntu is open source. There's no licensing problems with those products. It's just there are some products that are a little bit more aggressive with their licenses than others. Oh yeah, any other questions here before we go on to the platforms as far as what do we deploy this stuff on? No, we're good? Is this up the alley of what you were interested in? I don't know. I'm just going to keep going like it is. So this is what I've been using as far as building my services. from a platform specific. What I look at first is, can I build it myself? How hard is it? Does it already exist out there? If it does, how good is it? Can it do what I want? Will it continue to do what I want? Will it be supported? All those kinds of things. And I'm looking at that because, I have my own company on the side, and I also work for Microsoft, and I'm trying to keep in mind like what our customers want to do. Like I actually like think about you guys a lot more than you think I think about you guys. So like that's the way I'm tackling these things. And these are kind of the top ones that I've come up with as far as things that, man, it would really suck to have to do this on my own. So this Azure machine learning tool is the very first one that I go to from a data science perspective. You can write R code as well as Python code and deploy it to that, as well as it has literally drag and drop modules for doing machine learning. So a great example. Okay, I can write a neural network, that's fine. And I can write a convolutional neural network and like a lot of different variations thereof. But boy, does that take a lot of coding. Does it take a lot of effort? Now I gotta maintain it. This thing just has a little thing where I pick my data set, I drop the data set in, I grab the neural network, I drop it in, and I connect a little arrow between the two and magic happens. I was like, okay, so if I can get like the accuracy that I'm looking for, tool one, this is it. The only downside to it is its execution remains server side. So let's go back to the underwater submarine. Underwater submarine says, well, execution has to happen on the physical submarine itself, because if I need to be able to map the ocean floor and like obstacles. If I'm gonna hit that obstacle, I don't wanna make a server call when I'm out in the middle of the ocean to figure out if I'm gonna hit something. That doesn't make a lot of sense. But one of the crucial things that I would use this for in the underwater submarine example is when you're building the algorithm that figures out whether you're going to hit an obstacle or something that's on the ocean floor, you need to have a training set of information. Well, you need to take the hundreds of thousands of pictures and annotate those pictures with what's in the picture and where is it. Well, you have hundreds of thousands of pictures, and they're all in the server side, right? And now it's your job to annotate that. Well, what might be interesting is, let's find pictures that are interesting. What you can do is there's literally a module in Azure Machine Learning called anomaly detection. You can feed it some pictures and it'll say, hey, there's something weird going on with picture 746. Maybe you should annotate that picture first and use that as part of your training set. So when you think about the way that you're going to build your algorithm using this training information, you can start using some of these server-side components that may not necessarily be directly relevant to the physical device itself, and begin using these. And because this one's really quick to get up and running with, I don't want to spend a lot of time or maintenance on that. It's not part of my core business. But it is helped me get up and running a lot faster with building an underwater submarine that doesn't hit obstacles. So that's really cool. Then there's this Linux VMs thing. So I actually was, before you guys got here, was doing some examples on this new neural network training framework called TensorFlow. It works for more than neural networks, but anyways, it's this framework called TensorFlow. It's made by Google, and you can run it on your own stuff. But I want to target embedded systems, and NVIDIA is like, well, if you want to target our stuff, you can use a Mac or a Linux. But Mac or Linux. And then no, that was TensorFlow. TensorFlow was Mac or Linux. And then NVIDIA said, well, you can use Windows or Linux. So I was like, well, crap, we draw our Venn diagram, I'm stuck with Linux. So now I need some sort of super massive computer to train my image detection on and things like that. That might not necessarily be a target for this Azure Machine Learning yet. I can run those on these Linux VMs and get a test environment up and running for those types of tools, execute it there. It's also nice for cron jobs, really simple ETL process, since I'm writing a lot of Python code these days. Linux VMs seem to be pretty nice. This whole data lake blob thing is my #1 tool. I couldn't survive without that. What that tool is and does is it's just binary large object storage. Just store stuff, whatever it is, and we'll handle it. It's replicated 3 times around the US and 3 times in each data center. It's like, great. So this instance where my 12 terabyte RAID array went down at my house and I lost all my movies, Man, I really wish I had it up there right about now. Luckily I rebuilt it and now it does actually live there. But as far as like doing this training and this extra information, you stick your training information here for your data science and your data lake and blob. What happens is now you have to stand up either a Hadoop cluster or you can stand up an Azure machine learning module to do some training on that information, use that information, visualize that information. Maybe you're using one of these things like Power BI. Maybe you have a cloud-based SQL server that's got Polybase and you're combining multiple things together. The thing of it is that if you put them all in the same data region, they all live in the same data region. And internally, Azure has really nice networking, whereas like my house to like my compute cluster to one of my colleagues' compute clusters is like data's going at whatever bandwidth that Comcast has decided for us. Whereas if it's all up here, I'm finding that it's a lot faster. In fact, when I stood up a Linux VM and had to download this one massive package called Anaconda, it was done in a few seconds because, I don't know, whatever, the Azure pipe is much faster than my whole network. So that was really nice. So getting this data lake and this blob, I get all my data up here, and then I can build my algorithms and do all my development in this ecosystem, and it's actually accelerated my development time substantially. And then there's things like this thing called Jupyter Notebook. I didn't actually put any notes in here about, but it's like an interactive coding web-based thing, and I can host it up here, and you basically code in a browser and share code, that's pretty cool. And then this app services, that's kind of the deployment ecosystem. That's where you get things like Service Fabric, websites, web jobs. Those are going to be your primary deployments for any sort of environment. And I have an architecture diagram. I know I listed it out here, and I see some blank stairs, so I have a picture. In fact, I have another picture where everything's a present. So if you guys don't get the first picture, I've got another picture. I'm starting like really complicated, and then I'll try and like dive simpler. Maybe we'll do it opposite next time. And then there's the SQL and Power BI thing. Next up is actually the picture. So are there any questions from like, I want to go over this one questions and this one questions. Are there questions? No? It's
just a little, I think I know what you mean, but you keep mentioning training. Could
Yes.
you kind of expound on?
Yes, I will expound upon training. We're going to have to shift the camera to face this way because we're going to end up having to pull out a whiteboard. I hate to pull out a whiteboard for this, but it's the easiest way is to just, okay. So you guys know the function of a line. Who took like geometry? Who remembers geometry? Raise your hand if you remember geometry.
Yeah.
Okay. You remember this whole like y equals mx plus b thing? Yeah. Okay. So the function of a line. Let's draw a pretty graph here. This is a graph. You have your y-axis and you have your x-axis, right? And let's say we're plotting houses. This is square footage, square foot, and this is price. Okay. Now we have just a bunch of random houses all around here, and that's their points, right? Well, if we want to predict the value of a house, that looks kind of good, doesn't it? So this actually is y equals mx plus b, where your m is some value which defines the slope of this curve, and your b is your starting point here, right? So when you train this, you're taking all of your examples that you have and trying to minimize the error that this line has when predicting the value of those. So when we say training, what that means is I'm taking all the examples of all the information that I have and I'm pumping them into this algorithm that goes and basically minimizes the error of my predictions. So this is a very, very, very simple example.
So is that something that the platform or the language does for you, or you have to figure that out?
Azure Machine Learning literally has a little box, and you go, I want this, and it'll go and do that for you, and you don't have to figure much out.
But does it only work for certain functions or for certain?
You can do all sorts of ridiculous stuff, like image recognition, just tons of stuff. I've found some examples lately where they were simulating. They would take a video of a guy with a drumstick, like smacking and swiping all sorts of random things, and it would generate a sound wave using these types of techniques that actually matched the video so closely that I actually had issues determining the difference between the real video and the fake video. So, you know, when you, this is just super simple, and
Right.
like,
I mean, would it be able to tell you whether it's a linear or a quadratic or hyperbolic?
so there are variations. So you know, you could turn this into having like 100 different features. So instead of x, you have like z, whatever, and then you could have some n number of polynomials. But you have to be careful about how many polynomials you add as far as what order, because then you start, you know, you basically, you know, if you have 2 polynomials, you squared, then you cubed, and if you have 100 features cubed, 100 features cubed is like crazy.
So that's the human component. We have to decide how many polynomials.
Or you use a piece of code that generates n number of polynomials and say, hey, 6 polynomials, and then there's a way to automatically downscale it based on the shape. So like, I have a section in this talk specifically
Hey, if
around
it's coming
that.
up,
It's coming up. I actually have a picture.
Okay.
It doesn't have presence, but I do have a picture. Let's get to architectures, then we'll do a little dive into algorithm development. I figured we should know like what we're writing code in and where we're sticking code before we get to like, you know, that kind of stuff. I don't know, maybe we could start with that next time. So I told you I have a picture with presence. So remember this whole complicated scenario that I was talking about? And this doesn't even necessarily have to be cloud-based. This could be anything. But at the end of the day, you have information, which is a present, and it's coming from somewhere, and it needs to get routed to somewhere else. Usually you're going to store it long-term, so blob storage in my example, or Azure. So I stick a present here. This forklift also takes the present and sticks it over here. And it'll either send it to workers or send it to a dashboard. This dashboard could draw historical trends and hot path real-time information. We can also take real-time hot path information and send it down to workers. And it's all a present. And the reason I say it's a present, and I want to treat it like a present, is because you have no idea what you're going to encounter. You know, at least for me, you know, I'm working with customers, and some customers have like a smart water bottle I encountered. Another guy had this Russian-based HVAC that he converted into running a reverse osmosis machine on a yacht, which basically converts salt water to fresh water. You have no idea what people are going to do and what they're going to do it with. So I've just decided, all right, your information is a present, and it's just got to go around to these various places in some fashion, right? So that's kind of what this does. So if you think about it, you've got your present, it comes up, it has to get split out and duplicated, long-term storage, real-time dashboards. If it's really, really important and it really has to be attended to right now, you send it somewhere else. It could be a worker, or it could be another system saying server down, stand up a couple more servers. Who knows what it could be? It could be anything. I should have replaced him with like a question mark, but you know. So basically cold path, hot path, you got warm path, so forth and so on. So pretty much everything gets built out into interfaces. You have some form of messaging framework, so the package has to get up to the router, which has to get into the long-term storage, which has to go into the real-time analytics system. The real-time analytics system has to stick it into your real-time dashboard, which combines your historical information. And if it's important enough, your real-time analysis system has to take that and send it back down to a worker via your messaging system. So you have all these things that are ambiguous, and you don't know what your person has and what ecosystem. Greenfield development is so awesome. I love greenfield development because you just pick the easiest to use, but sometimes they have like stuff that you don't know what it is. So you have to kind of build interfaces for it. And you guys are probably familiar, you're a .NET group, so you're familiar with interfaces. You should just start using interfaces in analytics as well. So when you build your analytics from the ground up, use interfaces. I have a great starting point for you. Oh, before we get to the starting point, questions. I know, I have to do it. I have to do it on every slide so I know everybody walks away with what I wanted them to know. Okay, that's cool. So there is an actual code base out there that I've open sourced that takes care of a lot of the hard stuff for you. And this is the link to it. So it's called bioinformatics. When I started this project we were talking about doing, I don't even know if I'm allowed to talk about that project yet, so what are we going to call it? Bioinformation. So like think, connected people, like you're collecting biological information on people, and you need to do something intelligent with that. So I'm going to make up a scenario because I don't think I'm allowed to talk about the real scenario. And the made up scenario is we're going to determine heart attacks. We're going to connect somebody with a heart rate monitor that sends heart rate information to the cloud, and we want to predict whether or not they're going to have a heart attack 5 minutes from now. Cool. Okay, let's do that. So you could use this as a starting point for something like that, or you could use it as a starting point for anything else. It's currently under development. The main things that it takes care of for you is consolidating your security services. It consolidates your APIs so that they can be hit from any device, from anywhere, just standard web API type stuff. It also takes care of creating the interfaces and defining the interfaces for your messaging systems, for your routing systems, your real-time analysis systems. It has an example of how to do a real-time embedded dashboard. So like this thing, you can actually get one of these in like a mobile phone or a website. Or maybe you want to put it onto an embedded device that renders it on a touch screen. Who knows? It works. So that's why I put this up in here, because it's really complicated code and it really sucks to have to write it all the time. I've been writing the same code a million times, so I thought, what the hell, I work for Microsoft, let's just stick it out there because it's our tools anyways, it's going to accelerate your time to development or time to market for those things. So it's also under development, so be careful. It's very much a moving target right now. But some of the key things are, you'll see there are things like iDevice registration, iExperiment services. So there's built-in experimentation frameworks for this before it even gets up into the machine learning tool. So let's go back to the underwater sub example, right? We're taking video and we need to stick that video into the cloud. We need to run some form of experiment. Well, this framework that's built into it helps facilitate the sending of messages with annotations into your storage so that you can then do these training algorithms with it. So the core of this is to set up all the hard stuff that you normally have to write that has nothing to do with the value add, and accelerating your time with what I feel is valuable, which is doing something meaningful with information. Yeah, I did this slide. Isn't that just normal app dev? Yeah, most of it, yeah, it is. If we want to think about it, I'm just going to go ahead and say, I said ask audience on stuff, but that's because I had like 3 scotches and got lazy. Basically, the value to the business is not the way in which you move messages. It's moving messages. The value to the business is not storing the data or the security. It's not being hacked. It's not running into obstacles. It's mapping the seafloor. It's predicting if somebody's going to have a heart attack 5 minutes from now. So the point of this whole project is to try and accelerate the things that are not valuable to the business so that you can spend more time doing what's valuable to the business. Proposals. So steal good ideas and use them absolutely everywhere we can. What I really mean by this is in my time in video games, we built some MMOs. So a lot of this architecture is actually based off of MMOs. In regular app dev, where I built the food truck system. I'm not allowed to say the name of the company, but I built a food truck system. And we did a lot of security and API consolidation and intelligence there. And so I took a lot of the good ideas from that too. And then there's a lot of good ideas as far as open authentication and how to do a lot of these things. So let's go ahead and take things like interfaces and that kind of stuff and start applying it to analytics systems specifically. You can write good code for analytics, and that's kind of an attempt to create a framework for focusing on writing the analytics where you already have decent patterns in place, like dependency injection. Like there's now dependency injection in these analytics systems if you use that code base. And then I got really lazy. I didn't actually open Visio, so I thought I'd draw an architecture diagram of what the actual implementation looks like. There are a few kind of key differences. Each one of these boxes is like an actual component that maps directly to Azure. So these are just devices. These devices don't actually have to be devices. Those devices could be clients, those could be servers, it could be it's something that sends information. Then there's this thing called IoT Hub, which is your messaging service. It sends those packages around, and it has all this intelligent routing with it. Then there's a service called Stream Analytics. That's the one that allows you to actually do in-stream machine learning. You can do user-defined functions, windowing, a lot of really cool stuff, and it allows you to duplicate messages and send them to like 6 other places simultaneously. And the really nice thing is it's like 2 button clicks and it's up and running, and it can handle millions of messages a second. So that's really awesome.
That's an Azure service?
That's an Azure service. Yeah, this is probably one of my favorite. I think my favorite Azure services are Blob, Stream Analytics, IoT Hub, as well as Event Hub, and then what else are like the app services. Right now I'm using like the website, but I'm going to transition over to Service Fabric as soon as that gets kind of figured out a little bit better. That just does, Service Fabric just deserves its own talk altogether. So I'm not going to dive deep. Just think that's like super cool. So yeah, this is what the architecture looks like. It looks a little crazy right now, but basically all the arrows are where information is moving. You're taking really important information that has to happen immediately right now, that's server side, then in a compute box, and actually doing something more meaningful with it based on other information if you need to. And then you can use push notifications and send that down to either a cell phone or whatever. So one thing that I'm looking at now is doing real-time analysis of microclimates inside of nurseries. Nurseries, you know, the big like industrial-sized nurseries have like these greenhouses that are like, I don't know, they're way bigger than this room. And they actually have their own microclimates inside them. And if you just put plants in random spots, the plants are actually each inside of their own individual microclimate. So, you know, it's really nice to be able to send information to the workers. Hey, you should swap out this plant's position with that plant's position to better facilitate growth. That would be a really good example of, based on what we're seeing at this position from this device, we've sent it up through this path. We've decided, oh God, you know, the microclimate, there's something going on with microclimate. We got to do something with this microclimate. So we send it over to this compute box, and it goes and looks up who it needs to send messages to, so forth and so on. And then it goes and sends those messages down to the workforce and displays it out on a web server for the boss to know and, you know, see his updates in his dashboard and stuff. So that's kind of the main path. Other things that you'll see are, it'll go over to the data lakes that you can use it for auditing. You can also use it for training your algorithms that determine if it's important or not. You can put it into SQL Server 2016, do some manipulation with R, and then pipe it into Power BI, so forth and so on. So really cool architecture. I highly recommend. I put the slides up on my website, so I know it's not Visio, so it's not pretty, but like, you know, take a look at it. I use this exact architecture for almost everything now. And this is the architecture that this code base actually uses. So if you want to understand this code base, it's really helpful to understand the architecture. Okay, now we're going to do data science foundation. So what we've covered at this point is basically, yes?
Who's that guy?
I don't know, he came from the corporate, so there's like a corporate slide deck, and I really liked him. Because that face says a lot of different things. That face says, are you for real? Like, are you serious? But it also says like, huh, that's really interesting. So like, I like to use him to like annotate a lot of my, he's like my visual commentary on what I'm doing, and that face just is like, you know, 10 different things at the same time. So I really liked it. So I have no idea who he is, but he has the best face I have seen in a long time.
I thought it was somebody famous, I don't know.
No, he's just some dude. There's nothing special about him. Yeah, he's on YouTube here in like the next week or so. So at this point, I want to kind of review very quickly what we've done, because we haven't done a lot of like data science specific stuff. I spent a lot more time talking about what kind of tools and technologies are you using for data science, and surfacing data science into a production ecosystem. I think at this point, now that we know what tools and technologies and how to get it into production, let's take a look a little bit more closely at what kinds of things are we doing here. And you'll start to think, oh, I can use this for that, and I can use that for this. Now that you have a general idea of what tools and technologies are out there. So the first thing is data science kind of sort of needs data. If you don't have data, well, you're not really doing a whole lot of data science. You're probably just doing science, or I like to use the word pontificating, but like my wife informed me that that's not the correct usage of the whatever kind of word that is. I'm not a linguist, I'm an engineer. So anyways, you need data. You got multiple data sources. It needs to be prepped for either visualization or machine learning. And this is a really nice, I love the sales guys. The sales guys make the best slide decks. This actually visual came from a salesperson. I really liked it. Because it really demonstrates what I'm seeing out in the world right now. Like, people have got SQL servers that have transactional data. Then they've got these devices, and they've got like Hadoop. And then for some reason, somebody decided, hey, let's use this JSON data storage thing and SQL, and we'll have Hadoop, and let's like have this random table storage thing out there as well. And you go into a typical customer, and they've got like 30 different types of data storage services, and like, what is going on here? So if you want to do anything useful with their information, you typically got to get it into some form of like consolidated format so that you can start doing analysis on it. So usually you have to kind of start by ingesting all of that information, the typical ETL type process, and then you got to prepare it for whatever kind of visualization or machine learning needs, and then you can publish it out. I kind of like this workflow. There's a couple of other things like this analyze thing I fit training your models into and stuff as well. And then this consumption for your model, for your machine learning models is going to be an execution type thing, either on your device or from your cell phone or website or wherever it's executing. And then your visualizations will also be consumed via wherever they're being consumed from. But basically, abstract level, you got to get your information from point A into a consumable format for point B. And the other thing that I liked about this image is there's a feature in Azure called Data Factory, and this is their like logo thing. I don't know if you guys have heard of Data Factory, but a lot of this processing is actually fairly complicated to orchestrate if you're doing it for large customers. And Data Factory makes it fairly simple for large customers. That said, a lot of times you encounter small customers, and what I find that I do is I just stick a Linux VM, deploy some Python code, and set up a cron job. So, it's quick, it's dirty, it's not expensive, and it's not complicated. So, depending on your needs, do what you got to do. The underwater robot probably would use this, because the underwater robot has a lot of stuff going on. So, you need to have great data for data visualization. This actually is where the data scientist spends like 90% of their time, is getting data from that original cluster of what it all looked like and all the dispersed systems. Then when you finally bring it in, I didn't put any examples in here, but like these charges here, like disorderly in public and drug possession and battery, these were like cryptic codes, and I had to go talk to my buddy who is in the he's in the narcotics division for the FBI. And I was like, dude, I don't know what like a CBL 403 is. Can you please explain this to me? So I ended up, you get all this data and it's in some format and you're like, what the hell is this? Sorry, what is this? And you gotta get into this pretty format. This 90% of your time is spent doing this. So when I say like this section here, prepare, there's a lot of information where you're aggregating a lot of these sources together to actually get it into this format. And somebody said, is this the Snowflake format? It's not Snowflake. What I basically do is I build one two-dimensional table that maps specifically to a specific graphic, and we orchestrate the data pipeline so it's always up to date. So it's either a nightly basis or whatever. Okay, getting your information into that format. This is part of the descriptive analytics, and I kind of feel like that's a solved problem, so I'm not going to spend too much time on it unless there's questions on it. This is one of the things I use R for, actually. So like getting all the information into this format, this is like the thing that R is like super amazing at. So what else was I going to say? all the tools, things like, so you'll go onto like the Tableau website or the Power BI website, and they're like, we'll take all your data and we'll make it super easy to draw, pretty charts with. Only if it's in a pretty format. That's the thing. So by doing it and getting it into this like two-dimensional shape, that's crucial. Like the tools work great if the data's in a great format. Do that first. That's where you spend 90% of your time. And if you look at my code for like go to that R jumpstart thing, you'll see there's like 300 lines of code, and about 250 lines are getting it into this format, and about 50 lines are making it pretty and like drawing the visualization. All right. I told you I would have a slide on algorithm development. In fact, I'm sticking with the house square footage thing. So now that I have it up here, you have your typical algorithm development from a machine learning perspective. A lot is, the goal of it is to use the information at hand to build statistical models so that you have a little bit more of a defense as far as how and why you're getting the answers that you're getting. A lot of times I'm seeing code where it's like guessing. In fact, a lot of the code I used to write used to do that. We just like go look at the information and say, oh, it's over 75. I guess it's leaking. So that's not a good way to do things. Some of the first code I wrote was actually doing that, and I found out through, as an accidental data scientist. So started learning about these like linear models and these neural network things. And basically, at the very end of the day, no matter which one it is, you have some form of algorithm typically based off of a linear model. It's some variation of that at the simplest form. And it's basically, hey, we figured out there's 100 times the square foot plus 5 times how big your yard is plus 100 times whether or not it's a modern or updated, so a 1 for modern or a 0 for not modern, plus 50,000. So what you get are 100, 5, 100, and 50,000 are these trained weights. And what you're doing when you're training one of these models is that you're kind of going through and iteratively changing what each one of these weights are based on the previous error. And it's this long, process that I don't know if I have time to explain, to basically get down to, all right, this is the one. This is based on everything that we have and all the tests. This gets our error to where you're only about 3% off. So, it's a mathematical way of kind of creating great algorithms. And you can do a lot of stuff with this as well. There's more things like batch processing of sales transactions, different topic. What's really interesting to me is it's easily representable as matrix calculations. So, boy, here we go. So, how many of you remember linear algebra? You didn't think you'd come? Yeah, right. One person, 2 people. Okay, so basically, the way I think I actually have a better picture on like a different slide for this. Yeah, I have a better picture on. I'm going to explain linear algebra on a different slide because I have a better picture than this picture. So what you basically get is these x's are your data points, and this blue line is your prediction line. And basically, what you're going to do is say this is the size of square footage. You're going to say, okay, it's a 5,000 square foot house. You just kind of go up here, and then you go across. Oh, we're going to predict it's worth that much money. Well, your data is kind of moving around kind of weird. So even if you have a square footage house like this point here, is going to be like 1,000 square foot. You draw up, you'd probably say it's about half as much as it's actually worth. Maybe that house is in New York. So this is where the data scientist will also spend a lot of their time, is kind of diagnosing, debugging, and optimizing their algorithms. Here are, you asked about polynomials to represent your equation. Here's 3 different examples of an equation that can fit the data in 3 different types of ways. The difference between these 3 is you have the same input, square footage. The real difference is the number of polynomials applied to each one of those. So you have a couple of different features, and you can combine those features in different ways and then add polynomial representation. So think of it this way. If you're going to go buy a car, some important things about a car are How spacious is it? Does it have a sound system? Well, the combination of spacious and sound system might actually give it an accelerated value, and you square it or you multiply it by a bigger weight. Or maybe you square it and multiply it by a smaller weight, but it's just kind of squared. So it figures itself out as far as how it represents to minimize the error. So from left to right, we have a low order polynomial all the way to a high order polynomial. And there's some key issues here that I'm going to kind of explain. Here, simple y equals mx plus b, y equals mx plus b squared. Hey, that looks kind of good. That fits much better. You know, before we predicted here, now we're kind of in here more dramatically because the data that's representative of this is here. This fits really amazingly well, but has some inherent flaws. What if we get, you know, if you look at the pattern, it's actually more of like a logarithmic kind of thing. So you end up spending a lot of your time basically diagnosing what's called bias versus variance, which is how well does the data fit versus how well does it actually represent unknown values. Selecting your features, engineering new features, figuring out what combinations you want to have, which ones actually are representative of the same thing. Like maybe you have an example in inches and centimeters. Well, does that really matter? Or do they really, at the core of it, represent the same exact thing? So those are interesting things. And then there's this whole thing about hyperparameters. And hyperparameters are things that, like, if you apply the hyperparameter called regularization to this particular high order polynomial, you might end up with a model that looks more like this over here, but because you have a high order of polynomial, you have a lot of craziness and you're allowing it to get a little bit flexible while maintaining a more generic shape, if that makes sense. So you're going to spend a ton of compute time and cycles doing this. Man, I know I covered that kind of crazy. So I want to take a breather. Everybody kind of like take a breath. I'm going to take a breath at least. How does everybody feel about this? I know it was crazy math, but that's like, if you really dive into it, that's what data science is. It's a lot of math. It's a lot of understanding math. In fact, that's why I get back to the Azure machine learning tool, because this is really hard. And this whole algorithm like diagnosis section, believe it or not, there's a module in Azure machine learning where you can take this thing and say, figure it out and optimize, and it goes and optimizes. Is it as good as a hand-engineered one? No, but is like C# as optimized as somebody who wrote C++ from scratch? Probably not. Is it really good? Yes. So, you know, if it gets the job done and it achieves the level that you want, start there and tune as you need. And then, in fact, a lot of this stuff can actually be accomplished within that tool at these degrees. You just have to know how it works under the hood. Or you can take the little module. So you have two options. You can write the Python code to figure it out, or you can drop the module. So I really like starting there. Part of why I use that tool quite a lot. It's always my first hitter. But it's helpful to know this.
So in your role as a data scientist, what you're starting off with is you're building code based on an educated guess of an algorithm, and you're using these tools to adjust that algorithm as you're going?
Yeah, sure. It's really high level. Like, yes, you hit it from like a very abstract high level. Like generically, that's what I'm doing. There are like a bunch of.
But you have no idea which polynomial or which order of polynomial.
No, but you can. That gets to how you distribute your load and what you do and how you adjust it. So even on when you're doing an optimization algorithm, this is going to get really deep really fast. There can. How do we explain it in lamest terms? Basically, I'm gonna get to this again. So, like if you plot like the minimum a function can be, you typically get something that looks like a U. Find the minimum. Oh, it's here. Well, in some cases, your curve looks like this, and it's like find the minimum. Sometimes it finds here, sometimes it finds here, and it gets stuck. So you have to run it a couple of times, and what you get at the end of the day, actually, this is a good segue. I knew there was going to be somebody who would ask questions like this. Is that you actually get this whole linear algebra thing, because your input, it can be represented as a mathematical linear equation. So if we take a look at it, these are your incoming requests, and this is your trained model. Because your trained model is just like an array of numbers, you can just store that array, associate it with the performance values that it has, and pick the best performing one. So a lot of your time, when I say like a lot of your time is spent in this area, it's spent in this area because you're generating models, you're saving what that model is and associating it with the performance statistics. To do really fair actual scientific experiments, you need to use the same input training data and the same test data. So it's good to keep those separate from each other. But yeah, that's kind of how it works. You're going to end up having to do a bunch of guessing. And they're called regression models. The way that one of them works is it kind of picks a point, figures out what the slope is, goes in the direction of the minimum, and keeps stepping that way. So really, it's kind of guessing too. If you ran it 100 bazillion times, it's gonna get better because it operates off of derivatives, which is probably a little... anyways, yeah, so it can always get better, but you know, is 100 million bazillion times of running it really that much better than like 1,000 times of running it? And it's really who runs it the longest that gets the best performing algorithm. But you know, you've got a point of diminishing returns. Kind of the key takeaway I wanted from all of this is that training models is a long, complex task. And it takes a lot of heavy expertise to figure all of that out. What's really cool is once you figure it out, it's lightning fast because it's a single mathematical operation, especially if you're using a GPU. And a lot of this runs on some libraries like Intel's built that's super fast too. So that's really nice because it's all linear algebra. And if we go back to the submarine example, NVIDIA makes this really cool thing called a TX1. It's basically like a supercomputer like the size of a Raspberry Pi. It's like this big, but it's got 256 cores on it, which is just absolutely wild. It's 256 cores, and they're a specific type of core that's optimized for these kinds of operations. So really neat. There's hardware out there that's specifically geared for this kind of stuff. So you can do really, really good, really fast operations on huge data sets fairly effectively. Really long to train, fast to execute. Linear algebra, hire an expert is kind of the thing, or become an expert yourself. You know, the field isn't actually new. Data science is artificial intelligence. It's machine learning. We've been doing this stuff since the 40s, and you know, it's still hard and highly paid because you have to know calculus. Well, not as much anymore because you have these really cool tools out there. You just need to know how to do like this part, and this part's not nearly as hard. Any questions up to this point? I know I'm running like really tight on time. Okay, so that's kind of like data science. That's the data science foundations. I wanted to revisit the architecture one last time now that you know, so that we've done the architecture once, you know what the components, what kind of code. Now we have a little bit more of an understanding of data science itself. Let's kind of take a look at where certain aspects of the data science happen within the architecture now that we have an understanding of what the tasks are at hand and where they live in this terrible looking Visio diagram. So, okay, we got our devices on the bottom left, you remember that? And then all this is information moving to a bunch of different spots. This is our routing and intelligence engine. This stream analytics thing is actually one of the key places for execution of machine learning algorithms. The kind of hardware that backs this should be lightning fast. Okay, Microsoft kind of supports it, and it uses the Azure Machine Learning Toolkit, which has a bunch of geniuses writing the software behind it. I don't know how deep I'm allowed to dive in how that works, but it's really good, it's really fast. So this is going to be one spot where you're going to do that fast execution, because remember, really important stuff goes here. oh God, he's gonna have a heart attack in 5 minutes, or oh, the microclimate's not so good, oh, we just detected this image. That happens because you detected something in an execution at this point. Once we've detected that, it goes into this queue, comes up to this compute box that goes and aggregates that with other pertinent information so that it can actuate, remember the whole actuated analytics, and actually send messages down and do something useful about it. And then it can send messages to the workforce, which is our actuated component in this example. The other places, you could actually have some intelligence happening here, depending on what's happening. Who's the best person to send the message to? Well, Bob's over there and Joe's over there, but Bob's not so good at running because he's got a broken leg, so we're going to send it to Joe because he can run. So, okay, so now we know we're going to send our message to Joe. So this could actually be another execution aspect. You might have it running on the actual web server, servicing all sorts of different kinds of requests. Hey, which plant should I move? So, here is the hot path, right? This is the hot path execution. Over here may not necessarily be a hot path, and this may not necessarily be a hot path too. This could be part of your hot path, doesn't have to be. But here could be like a warm path. Joe logs in and says, hey, I'm getting in for the day. What should I do? Will says, oh, well, like plant A over there might, do better if you moved it over here, but it's not an immediate threat right now. So, Bob can go and move plant A over to the new location. A lot of your intelligence will happen. It could happen on this compute box and drive some of your predictions over in the dashboard. When somebody, like a business person, wants to take a look at their dashboard and say, hey, what kind of plant should we grow? That could be drawn here when they're looking at their dashboard. It doesn't, it's not an immediate thing. It's a, hey, I asked how many plants I should grow or what kind of plants I should grow. So we could do that computation again here on our warmer path and send it over to this dashboard that's asking us about it. Your training and your really long process really is going to happen here and in conjunction with this as well. So you're going to have a lot of administrative information in SQL. You'll probably have other data sources out there as well. Hopefully you drop all that into data lake or blob so that you don't hit your transactional database live to run a machine learning algorithm. Remember, complex, long times, long compute. Don't hit a production transactional database like that. Your operations folks will get very mad. But yeah, your training will happen here, and you'll have a web service or a virtual machine that you'll stand up that's going to kind of be in line and next to this, and that's going to actually do the compute. So the storage sits there, and then when you need to, you bring online a compute box or compute cluster of whatever kind of compute that is, and you do your training there. You generate your model. You can store your model here or update it wherever, whenever you need, or you use the Azure Machine Learning tool because all the sciencey stuff is way too hard. Any questions? No. I thought I'd finish with this because I thought a fair number of folks might get intimidated, and I wanted like a kind of consolidated list. Tools to make it easy. It's not exactly the easiest thing in the world to do. So data visualization, Power BI embedded. Power BI is great. You gotta get it into the right format. So I find I use a lot of things that are driving Power BI. I use a Python, Ubuntu, and Docker to write my ETL, drop it into data lake, and that will drive the visualizations. Data Factory does a lot of the bigger job. That integrates Hadoop and all sorts of other stuff. Visualization. Machine learning with cloud execution, Azure Machine Learning to train. It also can generate its own microservice. So actually, at the end of training an algorithm, you don't get like this linear algebra thing and you have to figure out how do I execute linear algebra. No, you just click a button and it publishes a web endpoint with the API key for you. Hit it from behind your own proxy. Perfect. So everything's produced with the click of the button. This is actually really effective, really good. I've gotten a lot of value out of this. I really like that. If you can do it with this, I start there. With client execution, there are two libraries that I've been using. There's CNTK and TensorFlow. You can train locally or in the cloud. It produces this thing that you have to figure out what to do with, but the cool thing is you can do anything with it. It's just like a matrix of values. So, once you know that, oh, I multiply this matrix of values with another matrix of values, you can now derive value out of it. So that's really nice. So you can produce a model, reconstruct on whatever client. It gets a little bit complicated, but you know, it's not so bad. Just learn a little linear algebra, or just have like one screen at home that has like your linear algebra cheat sheet, and one screen with like your code environment, one screen with like, you know, Google up or Bing. That's what I do. You don't figure this stuff out without those three tools. So yeah, that kind of breaks it down, I think, fairly well. Are there any questions around here, like what we're doing here? Yeah.
The machine learning that's on Azure, can you also get that library for your own machines?
Not as of today. That's why it's limited to cloud execution and cloud training. The nice thing is I put all my data in the cloud, so I usually train in the cloud as well, and then I execute either in the cloud or on-prem. The only times I'm finding where it makes sense to execute on-prem is in embedded devices, or if like politics or policy or legal stuff requires you to do so. But most of the tools for execution have compliance levels, so I'm finding that it's not so much the legal side as like the I don't want to because I feel like I don't want to, or a embedded technology scenario.
What about the cost though? Because you have a bunch of machines in your shop, that's different costs than running CPU.
Yeah, so this deploys a basically like a web service, and I don't even know how much it is. It's not expensive. I'd suggest looking at the pricing guide, but it wasn't even like $50 a month. It was more like $5. But like look at the pricing guide, because I don't look at the pricing guide as much. I just know like I prefer to have it up there because it's easier for me to deal with. It generates a lot of things like endpoint, static IP addresses. It gets me my API key. There's a lot of extra code and maintenance that I don't have to do. That I would have to do, and I would have to write, and I'd have to pay an engineer to do that. And the time to pay an engineer to do that is, you know, probably like 6 months. Well, an engineer is like $100,000. I just spent $50,000 to have it on-prem. It's not the cost of the server; it's the cost of the person to make it. So that's kind of where, and then to maintain it, so forth and so on. So I found, if I can, I do it there because I found holistic package-wise, I find it's cheaper. I like to do it on-prem because I think it's fun. I like to have my shiny toys, but I also like the embedded part. I spend a lot of time doing embedded because that's a core focus. I do a lot of what's called fog computing. So in fog computing, you have a combination of cloud intelligence, edge intelligence, and device intelligence. And you can't really get around on-prem, like avoiding on-prem execution in that environment. So I'd say look at it, see what you can do. If you can do it in the cloud, I found like 9 times out of 10 it's cheaper. It's just where do you stage, how much information, you know, work through that for like slide 3 or 4 or whatever. Work through that and assign numbers to it and like put up an Excel spreadsheet and say like, you know, include everything. I hope that answers. I went on a tangent there, sorry. Any other questions? I think the last slide is summary. We'll do this. Okay. Summary. So I like to tell you what I'm going to tell you. I like to tell you something, and then I like to tell you what I told you, because I feel like that's the best way. If I beat you in the head 3 times, you're going to remember it. So, you know, we did what is data science. I think we did pretty heavy on that. Bioinformatics. That's that project that has a living code base that takes care of a lot of the production code stuff, and not so much the data science, so you can spend more time focusing on data science. We talked about architecture and ambiguity, prepping for visualization, a little bit on algorithm development, and putting data science into production. And I would like to plug the Ascend Plus program one more time. So if you are building any projects that have anything to do with intelligence and cutting edge Microsoft technology, let me know. We can put it in the pipe and evaluate it. Might not get picked, but if it's not in the pipe, it's definitely not getting picked. So, you know, think about that. And that's it. Just open up for holistic questions. Or we can just give prizes. That's cool too. I know, like, I just talked for like an hour and a half, and like, it's 8:30, so.
All right, so here's my question. So we have a product that your orders, like any order entry system, okay? So how can we use the machine learning to see if the order is a good order? Because, and how do you train it to see what orders are good orders? So it can tell users, hey, that order is going through, that order is at some stage here, that looks like it's a bad order. Maybe some part of the product is bad, or some part of the order is bad.
What do you define? I think the first step is defining what's good and what's bad, collecting as much information around each order and labeling them or specific parts of them as good or bad and associating flags with it. So, you know, if we take this example again, where you have square footage, price, so forth and so on, you're going to have a certain number or sections of fields, and you can break it down. It doesn't have to be the whole order is bad, part of the order. So now you've defined part of the order. Which part of the order? Which parts of the order are you interested in? Now you create a series of features or fields associated with that. You have to convert those into some form of numerical number and be able to assign labels of good or bad to that. And what you're looking at basically is a binary classifier.
Well, an example would be for an order, you know how much the product costs you, you know the cost of the product, and there's an order, you know how much you're selling it for. So you can look at the profit on the product. If the profit is not in a certain range, it can be flagged as a bad order. So, for example, you can make no profit on the order. That, of course, would be a bad order. You want to make a profit on each order. Another example would be shipping costs for the order. You could calculate the shipping, how much it costs you to do the shipping costs, and that could have, because if something happens, that can take away from the profit also. So you find out you're unprofitable in order because the shipping costs and all of that. How do you grab those? I guess there's two examples of two things. How do you grab those and put them into the machine?
Yeah, so you're going to have to take historical information from that, and you know, really, I don't know if that's so. Sometimes it might look like a problem might be a machine learning problem, and sometimes it's actually not. Right now, I'm thinking a first step is that might not actually be a machine learning problem because you have hard, static, non-movable things. And if it's something like that where you can actually get access to all the specific information that drives a decision, then you actually don't have to come up with what those weighted values are. You know what those weighted values are. So you just kind of add it up and subtract and see, hey, is this enough money? What you might be more interested in is interesting orders that drive more profit. So if you have to make a decision between two orders or a couple of different batches of orders, maybe you get like a huge batch of orders, which one of these is more interesting, or which customer do we want to go after? Which customer do we predict is going to give us better orders in the future, and we should kind of treat that customer better or market better to that customer, so forth and so on. So like I think you're looking at the predicting bad orders versus good orders may be more of a static problem, whereas machine learning would be more applicable to focusing on groups of order generators and who's generating orders, and honing in on who's producing good orders and who's producing bad orders, and being able to action more specifically in accordance to that. I think that's the route I would start going with it.
Maybe like a recommendation system.
It would be kind of like a recommendation system. Yeah, I'm kind of just like tackling it like as I'm hearing it. So yeah, I think it's more of like it'd be like an anomaly detection, a recommendation, or what was the other one? I don't know. My brain's going right now.
So what we do right now is we use statistics, and we can find the standard deviation of, like, for example, the profits. And then we can look at that particular order, and we can see how many standard deviations is away from the group of orders, or the class of orders. And then if it's outside of 3 sigma, we then flag that as an order of the problem, for example.
Oh, okay. So yeah, you're probably looking at like an anomaly detection system. If you've got enough information to do that, then like an anomaly detection system can give you weird trend analysis over time for specific groups or orders, or various things like that. Whereas what you're probably you're able to detect just on one single item there, which so I don't know. I think my first step is let's take a look at the data. It's hard to say without seeing specifically, but
It's very specific, and everything you can do is very programming is intense. And we like to use machine learning, where we refer learns by itself. So you can have you can have more things looked at and get better feedback than what we have right now, which if it's not programmed for it, it's missed.
What I would say is, so my website, if you like just take the middle part, DA Crook, and add an @Microsoft.com, my email address is my website name, just @Microsoft.com. Send me an email with that like request specifically, and that sounds like, remember I was talking about the Ascend Plus thing, and we've got engineers and we're looking for projects specifically in this area. To me, that sounds like a perfect fit type of project, and I may be able to get engineering support for that using like the Azure Machine Learning tool.
Okay, sounds great.
Yeah, so send me an email and we'll follow up. Any other questions?
A lot of the ERP and short of somebody going in through BI, looking at regions of customers, does Azure have, is it relatively easy to set up where you can pump some of this data through and you can request certain types of data that you can have? And whether it be profitability, time to manufacture, those kind of things. Are those boxes that you have out there, are they pretty flexible or are they
Now you can move all those boxes around. Like I would say what it sounds like to me is not that problem, but more like this one. This guy here. So what this is, you got a bunch of stuff in some format, you send it through this pipeline, and you get into a more consumable format, and it does that orchestration for you, more like the scheduling and the stand-up and creation and provisioning of like the compute nodes that you need. And it's like you can take these modules and you can move them around. I like to think of it as Legos. Like I did a talk on Azure where I basically kind of described every component as a Lego, and by the end of it we built like a Lego like castle or something. And that's kind of like how it works, really, is that you have basically just think of it as a bunch of building blocks, and you can take these building blocks and connect them to each other in interesting ways to achieve the results that you want. If you're trying to just take some information and transform it into, you have some, who knows what kind of information, you want to get insights out of it as far as like sales or whatever, you would probably want to go through one of these pipelines, especially if it's in disparate, like distributed systems. Like you have like an Oracle and like somebody else owns some of the data, so forth and so on. But that particular feature is called Data Factory. I'm going to take one last question. If there's one more question before I call it quits. If there's no question, I'm going to call it quits. That's it. You lost your chance. Yes. It doesn't feel complete unless somebody claps. I don't know why. It just doesn't.